So I think others are still joining. So we will wait for a few minutes for everyone to join. Meanwhile, I will answer few queries. One I have received in email about marginal independence. So the question was how the marginal independence is calculated. Last class we had seen the way to calculate conditional independence, way to decide conditional independence and marginal independence via D-separation algorithm. That 5 steps. So same steps apply for marginal independence also, but independence is confirmed if there is no path between the two nodes under question. So if A and B, if there is no path between A and B, then they are independent, right? Okay, Urjit is also asking, can we go with marginal? Let me share the screen again. I think we are discussing uh, from here. Let's say we are talking about Markov bracket and all. Before that, we talked about marginal independence. So if you see, the question was, are D and E marginally independent in this graph? We said that D and E are conditionally independent given C. So for that, we started with a graph of B, C, and D and their parent and did all the things. So let us try to, I think I didn't draw the graph for marginal independence. That's why there is the confusion. So let me cut paste and do it for marginal independence. So let us ask two questions here. First is, D and E marginally independent. So I will follow the same process. So I will again create a graph of D and E and its parent. Their parent, so that is C. So this will be the graph, right? So the node under the question, D and E, their parent, moralize them their parent. Here there is only one parent, so no problem of moralizing. And remove the direction arrow. So directions are also removed. So this is the resulting graph after all the steps. Are you with me, Urjit?
Yes, sir.
Okay. So now the question is there after doing all this, after doing this graph, the question is, we see that is there a path between D and E?
No, sir.
No, there is a path, right? You can reach from D to E via C.
But sir, it is via C.
Yeah, but there is a path, right? There is a path between D and E.
Yes.
So there is a path. Answer is yes. And hence, if answer is yes, means that D and E are not marginally independent. To conclude about independence, the condition is that there should not be path between the two nodes under the question. Are you with me, Priyank? I think Priyank also had this question.
Yes, sir.
Now let's ask another question. Are A and B marginally independent? So what you do again, we pick up the node under the question and their parent. So the graph would be something like this. They do not have any parents, so it will remain A and B like this, not connected. The nodes are not connected. So the what will be the answer? Again, and
Yes,
after
they are
doing this graph,
margin.
please, yes, is there a path? Answer is no. Since the answer is no, it means that A and B are marginally independent, right? So here, remember that wording that I'm using. So in first case, I'm saying that D and E are not marginally independent. A and B are marginally independent. So we are commenting only on marginal independence. We are not commenting on dependence. So this technique that we are using is only to measure independence. It does not comment on dependence. So after this, we cannot infer that they are dependent on each other, but we are just saying that they are not marginally independent or they are marginally independent. So indirectly, you can say that they are marginally not independent, means they are somehow dependent. But a way of saying here, and the algorithm is limited only to detect the independence. Right? So that's why D and E are not marginally independent, A and B are marginally independent. So I think I have answered the question. The process remains same. It is same as conditional independence. But when you talk about the conditional independence, there is a third variable also on which you want to check condition. So if I ask the question about conditional independence, I would ask, are D and E conditionally independent given C? Or are A and B conditionally independent given C? So in that case, your graph will be different. And since your graph is different, your answer will also be different because there will be a path. So I can say A and B in this graph, I can say that A and B are marginally independent, but they are not conditionally independent given C. Right? On the contrary, D and E are are conditionally independent given C, but they are not marginally independent. Right? Is this clear, or do you want me to repeat the sentence?
Clear, sir.
Okay. Yes, so that was the story of conditional and marginal independence, and from there we concluded the last lecture with the notion of Markov blanket. We said that in a large Bayesian network, if you want to calculate probabilistic outcome of a random variable, given everything else, then you don't need to worry about the entire network, but you just need to look at the neighboring nodes of that random variable. These neighboring nodes are sufficient to make decision about the random variable. So that helps us in reducing our computation. And we discussed this last time because we want to exploit this idea to discuss about the sampling technique, a very important one called gift sampling, which we are going to discuss today. So with that, we'll start with gift sampling. I'm still waiting for a minute. If you have any questions so far in our discussion so far, so if whatever we discussed last time in last two lectures, if it is clear, then gift sampling is very easy. But if there is any doubt, please stop and ask me. if there is any doubt. I'm still waiting. So it is important to get the background clear. After that, the strategy would be very simple. Okay, so let's try to see what we discussed so far. We were talking about approximate inferencing technique, where we talked about random sampling, rejection sampling, likelihood weighing, and now we are going to talk about gift sampling. So we did one thing, that we randomly generate sample to answer inference questions. This is what we have done in random sampling, rejection, and likelihood also. And from your algorithm course, you know that the kind of randomization that we have used is Monte Carlo. Right? Remember, there are two kind of randomization algorithm: Las Vegas algorithm and Monte Carlo algorithm. What is the difference between two? Can anyone answer the difference between Las Vegas and Monte Carlo algorithm? Las Vegas gives always gives correct answer, but running time can be variable. On the contrary, Monte Carlo may give wrong answer, but running time is always fixed. So if you see in our sampling technique, our samples are always generated in constant time, though some sample may not be good, but we can generate. So that is called Monte Carlo idea. Then we introduced conditional independence and marginal independence, and we define a Markov property called Markov blanket. Right? So we say that if you want to decide about B, you only need to look at the neighbors of B, that is B, C, G, E, and F. So in a graph, it is Markov blanket. On linear graph, a special kind of graph where the nodes are arranged linearly, it is called Markov chain. For example, if you are given a chain of 5 nodes A, B, C, D, and E, as shown in this figure, and you want to calculate probability of E, and if you make an assumption that probability of E given A, B, C, D is equal to probability of E given D only. That is the last node that is on which E is dependent. So if you are assuming this linear chain graph, then E given D is equal to probability of E given everything else, right? So this is called Markov chain. Similarly, for graph, here you can say that H is independent of G and D. Just to make sure what we discussed last time is clear, we can say that H is independent of G and D given E and F. Right? So this is Markov chain idea of Markov chain and Markov blanket. So Markov blanket is defined like this. A random variable depends only on parent, children, and spouse. So try to read this word parent, children, and spouse in terms of graph. So parent means the node just above the random variable. Children means the node just below the random variable. And spouse means the node which are common parent. For example, for H, E and F, it depends on E and F. So E and F are spouse node. D is parent of E, F is spouse of E, and H is children of E. So if you want to decide about E, you need to look at parent, that is G and D, children, that is H, and spouse, that is F. If you know G, D, F, and H, then you can decide about E. So this is simple way of understanding or figuring out the Markov blanket. A random variable depends only on the parent, children, and spouse. So in our example graph D, the node D depends only on B, C, G, spouse node, E and F, children node. So B, C parent, E, F children, and G spouse. It only depends on five nodes. And A and H, it becomes completely independent of A and H. Right? So D given A, B, C, D, E, F, G, H, it becomes D given Markov blanket of D. We'll use this notation. So instead of writing B, C, E, G, F, I can say it is Markov blanket of D. Or contrary, if I write Markov blanket of D, you should be able to figure out that it means that parent, children, and spouse of D. That is B, C, E, G, and F. Is this clear? How to figure out Markov blanket? Okay. So now we did two things. One is Monte Carlo, that is randomization. Second is we made assumption about conditional independence, which is Markov property. So kind of algorithm that we are going to discuss now, the gift sampling, fits in a broad general category of algorithm called MC method. And this MC stands for Markov chain Monte Carlo algorithm. So these are called Markov chain Monte Carlo algorithm. This is a good or very frequent term in statistical machine learning. So if someone asks you what is MC algorithm, then one example for us is Markov chain Monte Carlo method, which we are going to use here in approximate inferencing. It has other applications also, but in our context, we are talking about approximate inference. So let us see why we use this method. So one is we do not want to draw or reject too many samples randomly. That was our argument for rejection sampling. Second is we do not want to put probabilistic weight around samples. Right? So that was our second argument. So unlike the likelihood weighing where we were calculating probabilistic weight. And second is we want to keep evidence or condition variable fixed. So we take some idea from likelihood sampling, particularly the one where we are keeping the evidence variables value fixed. But we do not want to do this probabilistic weighing of likelihood. And also we do not want to reject samples. So how do we do? So that answer is gift sampling. The procedure of gift sampling is as follows. Step number 1, fix evidence variable, similar to likelihood weighing. Step number 2 is randomly choose values of other variable and draw first sample. So first sample is drawn randomly, the Monte Carlo way of doing things. Then the next sample will not be drawn randomly, but the next sample will be generated from the previous sample which you have generated randomly. And how do we do this? So for each non-evidence variable, now I believe you know what is evidence variable and what is non-evidence variable. Evidence variable appear as after given in the probabilistic query. So probability of B given A, B, then A and B are evidence variables. Right? So that is, these evidence variables are fixed. And for each non-evidence variable, calculate the value by keeping values of other variables same as the previous sample. So we'll flip one variable at a time. We'll calculate value of one variable at a time, and we keep on repeating this until all variable values are changed. So first, randomly assign value to all non-evidence variables. Evidence variables are anyway fixed. So first sample is randomly generated. Then believe that, then take out one random variable and try to calculate value of that random variable, believing that all the random variables value is correct. So assume that the randomly generated values are correct, and as per those value, what can be the value of this random variable, particular random variable which you are focusing on, and flip that value if required, and then keep on repeating this process for a sufficiently large number of times, and you will get new samples. Let us see through an example that will be more clear. Let us say this is our Bayesian network of four nodes A, B, C, and D, and with the probability distribution as shown on your screen. You may note down this thing. We might use it for our calculations. So please note down this value. I will wait for a minute or two for you to note down the thing. Have you noted this down? Okay. And also note down these steps. These are pretty simple steps. Language might sound difficult at this stage, but with example, it should be clear. Also note down this step, or maybe you can take screenshot of this. Yes. Are the steps noted, or you want it to be on screen for some more time?
Just a minute, sir.
Okay. Yeah, finish it.
Done, sir.
Okay. So I believe most of you have noted this. Now let's see how it works. So now the query variable is probability of A given B is equal to true and D is equal to true. Let us say this is our query. And we want to do approximate inferencing. And for that, we want to generate samples using git sampling technique. So can someone answer me which variables will sample and which variables will keep fixed? If this is the query, if query is probability of A given B is equal to true and D is equal to true, then as Priyank and Dev, and I believe many of you are thinking B and D are fixed because they are our evidence variable. And we know that we want to count only those samples where B is equal to true and D is equal to true. So keep them fixed. And which variable we are going to sample? A and B. Sorry, A and C. B and D are fixed. We want to sample only A and C. So let us see how it can be done using gift sampling. Step 1 of gift sampling says that fix the evidence variable, which I have marked in red. B is equal to true and D is equal to true, and randomly sample remaining variables. In this example, remaining variables are A and C. And we have randomly sampled it, and A turned out to be true and C turned out to be false. So this is our first sample, randomly generated first sample. Just to give you idea of whether we are consistent with the algorithm or not, let's see this. Step 1 is fix evidence variable. Second is randomly choose value of other variables and draw the first sample. We have finished step number 1 and 2 here, and we got this sample. TTFT. A is equal to true, B is equal to true, C is equal to false, and D is equal to true. This is our first sample. Now let us see what algorithm tells us. The next step is, for each non-evidence variable, calculate the value by keeping values of other variables same as the previous sample. Update the value and create new sample. So here, for each non-evidence variable, the statement says that we want to do it for each non-evidence variable, that is A and C. In which order we should take A and C? From the top-down scanning of the graph. If you remember, in random sampling and likelihood weighing also, our order was top-down, left to right. So top variable first, and right and left variable before right variable. So this is our standard practice. So we will follow the same order. So let us first sample A. Now we want to decide value of A. So we are assuming that all other variables are given this value of other variables, that is B is equal to true, C is equal to F, and D is equal to true. We want to decide value of A. So in other words, what we want to do is, we want to calculate probability of A is equal to true given B is equal to true, C is equal to false, and D is equal to true. If this comes above 0.5, then we will keep A is equal to true. If this turns out to be less than 0.5, then we will flip A to be false. Right? Are you with me so far? So sample 2 was probability of A is equal to true given B is equal to true, C is equal to false, and D is equal to true. The same question which I have written here. And how do I calculate this? I make use of the Markov blanket of A. Let us see what is Markov blanket of A. A is here. So what is Markov blanket of A? A, B, and C. This red area, which I have marked as Markov blanket of A. So probability of A given B is equal to true, C is equal to false, D is equal to true is equal to probability of A is equal to true given B is equal to true, C is equal to F using our Markov blanket property, which turns out to be joint probability of ATBTCF divided by probability of BTCF. And we know this subgraph at ABC. How do you calculate this probability? AB joint distribution of ABC. Probability of B given A into probability of C given A into probability of A. Right? So this is the probability. Probability of B given A into probability of C given A into probability of A divided by probability of B and C, where we want to marginalize over A. So again, probability of B is equal to true given A is equal to true into probability of C is equal to F given A is equal to true into probability of A is equal to true plus probability of B is equal to true given A is equal to false, and so on. So all cases where A is false. Same thing which we did in naive-Bayes classifier, right? So we are only looking at the subgraph of A, B, and C. We are only looking at this subgraph of A, B, and C, and we are focusing on joint distribution of A, B, C to calculate probability of A given B, C, which turns out to be, I have pre-computed this, but I wish you also try it. So I will wait for you to finish this computation and see if you get the same answer as me or not. So usually I prefer to write with you, but since the content is a bit heavy today, I had pre-calculated notes so that we can move a bit fast. But that should not stop you from doing computation on paper.
Sir, yes, here we can see like a numerator probability of A, B, and C. Here, like B and C are conditionally independent when A is given, and in denominator, B and C, because B and C are marginally dependent. So we have
Yes.
to expand like that only.
Exactly. So now you got the idea clearly. Yes. So because B and C were not marginally independent, and they are conditionally dependent on C. Sorry, B and C are conditionally dependent on A. So to calculate the probability distribution, we have to bring in A in your formulation. That is called marginalization over A.
Okay, so we got.
Yes. So have you finished the computation? Are you getting the same answer? Okay, Dev is acknowledging. Let's wait for 1 more minute to see what others are getting as an answer. But I guess the second sample is clear to everyone. Let us move to the third sample. So after the computation, came we calculated probability of A is equal to true to be 0.845 or 844. Okay, so more or less same. So A remains true. So after computing this probability, A remains true. Now what? A is updated. Updated means its value is not changed, but we have computed and update the value. Now the next task is update the second random variable, which is not an evidence variable, that is C. So now calculate for C. While you are calculating for C, you believe that A is equal to true, B is equal to true, and C is equal to true. Or given that A is true, B is true, and D is true, what is probability that C is also true? So we ask the question, what is probability of C is equal to true given A is equal to true, B is equal to true, and D is equal to true? Before I show you the computation, I would like to see answer from you. What is the simplification of this with Markov blanket property? The probability of C is equal to true given A is equal to true, B is equal to true, and E is equal to true is equal to what? Does Markov blanket help you here? If you look at the Markov blanket of C, it covers everything, right? A, B, and D. So you have to calculate that. So it will be something like this. In denominator, you will marginalize over C. And you want to put the complete joint distribution of C, A, B, and T. Can anyone write formula for this complete joint distribution? What is probability of C is equal to true, comma A is equal to true, comma B is equal to true, comma D is equal to true? How do you break down into break this down into different probability? You need to look at this graph and write down the probability. So this probability of complete joint distribution of A, B, C, D is probability of B given BC into probability of B given A into probability of C given A into probability of A. Right? The things that we used to do. Here's step number 3. Look at this formula, calculate the value, and tell me what values you find here. You need to put this value from the conditional probability table. The values are already given in the table. If you have forgotten, I can show you the table. The table is here. Table of B, C, probability of D, probability of B, probability of C, and probability of A. Priyank says, sir, here why we did not consider Markov blanket. We did, but the Markov blanket of C turns out to be all A, B, and D. Right? Remember definition of Markov blanket? Markov blanket means parent, children, and spouse. That is all three A, B, and D. So probability of C given A, B, D is same as probability with Markov blanket also. You are not reducing any variable in that. Yes. So once you compute this, you will get something like this: 0.75 divided by 0.857. Please do it yourself and tell me if this is correct. My calculation can be wrong, so please someone please verify this. So are you also getting the same answer? So how many of you are getting this answer? Okay, Urjit is doing. Okay, let's wait for a minute. Okay, Shail is getting 0.75 as the numerator or final answer. Okay, final answer. Okay, then it's quite a bit different than mine. Okay, Urjit is also getting 0.75. So maybe, okay, or maybe this is not slash, but I think I might have ended up computing two things. But anyway, it is 0.75. Let's say this is the correct answer. And 0.85 is not correct answer. Let's discard that. If you're getting 0.75, then you would like to assign the value true to the random variable C, right? Point 0.7 probability of C is equal to true is point is 0.75. So C becomes true. So the next sample, for the next sample, value of C will change from false to true. Okay, when we say false, then that is user answer is asking. So whichever probability is more than point in two outcomes, in case of binary, the probability which is greater than 0.5 will be assigned. If probability of false is more than 0.5, then false will be selected. If probability of true is more than 0.5, then true will be selected. In case of multinomial, the largest probability, that value will be assigned. Have I answered your question, Antri? Yeah, okay. Yeah, so this is how it happens, and we keep on repeating this. Usually in gift sampling also, thousands of samples are generated like this, and actually initial thousand samples you just discard, and then you reach to a stable distribution. So what we are trying to do is we start with a random sample, and we keep on updating, flipping value of one random variable at a time until we reach to a sample which is true to the underlying distribution, that is under our conditional probability table and Bayesian network graph. So we keep on repeating this process thousands of times, and then we start collecting samples on which we perform inference. This gives sampling. Before we end, we have some time, so I will take one more example. Not here. We'll talk about this. So just to revise, in deep sampling, we fix evidence variable, we randomly initialize other variable, then we sample one variable at a time and change value of that variable. We repeat this sufficient number of times until the samples represent true distribution. Until this, we know that first thousand of time was something, and then we start repeating. So let us try it for this example. Now I'm not doing the computation. I want you to do the computation so that uh, we can be sure that you got the point. So the first sample that I have generated is everything is false. And the inference question that we are asking is saying that probability of J given Mary has not called and earthquake has not happened. And this is first sample. Everything is false. So what will be the second sample now? You start with, in second sample, which variable you will consider? You will calculate, you will flip B in the second sample, given that everything else is fixed. So the inference question that you are asking in second sample is probability of B is equal to true, given that E is equal to false, A is equal to false, J is equal to false, and M is equal to false. Right? And while calculating this, you look at the Markov blanket of B. So you calculate only probability of B is equal to true, given A is equal to false and E is equal to false. So calculate this, keep on repeating, and see what answer you get. I think Urjit is with me. Most of you got that idea also. So Urjit, is the final answer true? Okay, you are doing it. Okay, do it. Let's see what answer is. So in my computation, the final answer was B remains false. Bhavik is asking, can you please write expansion of equation? Yes. So probability of B is equal to true given A is equal to F false and E is equal to false. So now if you want to write the expansion of this, I need to look at the joint distribution of B, A and E. Right? So joint distribution of B and A and E is known to us. It is equal to probability of A is equal to false given B is equal to true and E is equal to false into probability of A is equal to false into probability of E is equal to false. Right, Davis? So we just need to look at the graph, a subgraph of that particular random variable. In our Markov blanket of B, if we say B, A, and E are the three variables, then look at that subgraph and write the joint distribution of that subgraph. Are you with me, Bhavik? Is this clear? Of course, in denominator you need to marginalize, but in numerator you can do it like this. So that is our second sample. And what we have done is, while calculating probability of B, we will use knowledge of conditional dependence and independence to calculate probability of B. Right? So the Markov property, Markov blanket that we discussed, which is parent, children, spouse. I'm just revising things for your reference. So Markov blanket of B is A and E. And similarly, Markov blanket of J is A and M. So once the B is sampled, in second iteration, what we do? Here we have sampled B and we get the answer, let's say false. If you complete it and if you get new answer, please let me know. But for now, let's say we got the answer B is equal to false. B remains false. I need some other color. So this was our second sample. Now in third sample, we ask question about A. Assuming that everything else is same, means assuming that this is false and this is also false. So now the question that we are asking is, in third iteration, the question we are asking is probability of A is equal to true given everything else is false. There was no burglary, there was no earthquake, neither John called nor Mary called. Everything else is false. And now we look at Markov blanket of A, which is unfortunately everything. So you cannot reduce any variable. And I will not do this computation then. You do it, right? So you got the point, I guess. So now calculate this, update the value of A. Then after updating the value of A, whatever value you get, put it here. And then update value of J. And so on. Okay, Shail wants me to zoom the diagram. So keep on repeating like this, and that is gift sampling. So I think it is time. I will wait for 1 minute or so for you to finish the computation. And please ask me if you have any questions. Yes. So is this clear to everyone? Are there any questions? Okay, so if there are no other questions, we will stop here. And with this, we will stop discussion over supervised learning in Bayesian network. From next lecture, we will move towards unsupervised learning. Again, we'll start with a reference of Bayesian network, but then we'll also discuss unsupervised learning in general. So from next lecture, we are starting a new chapter. I will end here. Thank you.